All right, everybody, let's get today's program started. Good afternoon, folks. Welcome to the Lunchtime Discovery Series. As always, it is good to be with you for another edition of our exciting program. My name is Chris Smith. I work at the North Carolina Museum of Natural Sciences, which is bringing you this fantastic broadcast right here on your YouTube screens, wherever you happen to be out there in the world. Maybe you're on the moon watching today. Well, nobody's out there on the moon watching today. Anyway, glad that you're here. We've got an exciting program for you. The folks over at the Office of Environmental Education within the Department of Environmental Quality have, swung for the fences today. They've gone and found fantastic guest speaker for today's Lunchtime Discovery Series program. Of course, they go find fantastic people every single week. We're here almost every Wednesday at noon, hearing from interesting people who are doing really fascinating and interesting work out there in the worlds of science and nature. So I'm glad that you're here. By my count, I believe that today will be the last and final Lunchtime Discovery Series presentation of the calendar year. So I just want to take a moment to say thanks, everybody. If this is, in fact, the last one, I think I got it right. But I'm so glad that you all have spent the year with us, and we're looking forward to a 2024 full of science, nature, learning, and more. I'll be here, and I hope you'll be here too. And I don't know, maybe we'll hear from our guest speaker even more again next year. I'm really excited for today's presentation. Space and space stuff is what got me passionate and interested in science from a very young age, even though I never went to space. I got pretty close. I work at a museum, I suppose, but not as close as Dr. Amy Fagan. Dr. Fagan is an associate professor at Western Carolina University in Geosciences and Natural Resources, and joins me now. Hi, Dr. Fagan.
Hi, Chris. Thanks for the invite. It's really nice to be here. So I'm out in Cullowhee in the western part of North Carolina. So that's something that always confuses people is how do we have a Western Carolina? It's in the western part of North Carolina. And I'm surrounded by some of my favorite space stuff. So I've got meteorites tucked away in my office, and I've got my Lego sets joining me. So I'm in good company, even though I also have not been to space.
So few of us have. So, well, I'm excited. One, because it looks like you've got like the best Lego sets.
I think I do.
But also I'm excited to hear your expertise on moon science and earth science together.
Yeah, absolutely. It's one thing that I think a lot of people don't realize is that we can learn a lot about early Earth just by studying some of the things that are on the moon. And so that's something that's usually new to other people.
Fascinating stuff. Well, I'm excited to hear your presentation. I'll turn it over to you.
Okay, great. Let's see if I can get it to share the screen properly, and it will be a miracle. Oh, I think, wait, let's see. Present. Are you seeing the correct presentation, or is it in presenter view?
It looks good to me.
Fantastic, except I started not on the first slide, so. Everyone makes mistakes. It's an important lesson for kids, right? So my presentation today is called Visiting a Piece of Home, why it's important to go to the moon, and how it can tell us about Earth's early history. So I'm going to talk a little bit about what we've learned about the moon, how we've learned what we have about the moon, and then a little bit about how it ties in with Earth and how we can know about Earth. I'll also, at the very end, talk about, okay, well, what's next? For the moon. So we'll talk a little bit about the Artemis campaign, which is the next human landings on the surface of the moon will be through Artemis. On the left and right side of my slides, you'll see some pretty color pictures. On the left side, this is a photograph of a basalt. So it's a volcanic rock. It's a meteorite from the surface of the moon. And this is taken at a particular type of light on a microscope using two polarizers. And as the light filters through the mineral, it'll split into two rays and then interact with each other. And when it hits that upper polarizer, just like with your polarizing sunglasses, we can get really beautiful colors. So it's a work of art, but we also use that to help us identify the different types of minerals, which gives us information about the chemistry. We can determine what formed first in a rock and things like that. So there's a lot to learn about samples. So this represents basalts on the left. And that's one of our main rocks on the surface of the moon. And then on the right is an anorthosite. So that's mostly made of a mineral called plagioclase feldspar. And we have both of these types of rocks here on Earth, but it's these two examples here are kind of representing the two main rock types that we can even see from here from Earth on the surface of the moon. So we'll talk a little bit about that. All right, so let's get us started with how we actually know any of this. And so if we look at these two maps, we've got on the left is the near side of the moon. And so the near side of the moon is what we see every night. Well, every time that there's a full moon. So the moon and Earth are tidally locked, which means we always see one side of the moon. And on the right side of your screen, let's see if I can use my cursor over here. This is the far side of the moon. So it's not the dark side. It does get sunlight. So it is called the far side of the moon. Superimposed on top of these are some landing sites for human missions as well as robotic missions. And so here on the pink, we've got the NASA missions. The square are the robotic missions. Okay. And then the dots are the human missions. So these were from Apollo. So the robotic missions from NASA were called the surveyor missions. In the teal boxes are missions from the Soviet Union. Those were called the Luna missions, and those were all robotic. So they were not human missions. We also have Chang'e. This is Chang'e 5 from China. We have another one here on the lunar far side. The cursor is not working very well. Let me do this. There we go. Over here on the far side. So those two are landings from China. And then very, very recently, India joined a group of very elite robotic landers to safely make it to the lunar surface. There have been lots of other things that have been launched to the moon, but these represent the soft landings. Things have either intentionally been crashed into the surface of the moon so that we can learn about it, or crashed not according to plan. So if we look at these two images of the moon, you can see on the left side in particular, so again, this is what we see at night, the black parts, that's your basalt. So that is what we see on the image on the far, far left in that microscope image. And then the lighter colored material is the anorthosite. And so that's what we see on the far right side of your screen in that microscope image. So even from here, looking up at the moon, we can actually see that there are compositional differences. But it also means that if we're looking at our Apollo samples in particular, we have a little bit of bias potentially in our samples. So all of our samples that were returned from the Apollo missions are all from the near side. There's only been one thing that has landed successfully in a soft landing on the far side of the moon, and it was not a sample return. So all of our samples that we know very, very specifically where they were collected and have that provenance were all from the near side. And if you're looking at these two images, you're probably thinking, they don't look the same. The near side looks very different from the far side. So that's something that we have to take into account when we are using the samples and learning about them. Luckily, we have meteorites, and meteorites are great because they come from random places on the lunar surface. And so we can get a little bit more compositional diversity than maybe what we have in the Apollo collection. Let's see, clicking to the next page. Whoops. I went too far. There we go. This is what I wanted to do. All right, so another thing that we need to keep in mind when we look at the samples is the distribution of where those samples came from and how far apart they actually are. So if you took the Apollo landing sites and scaled it appropriately to Earth, this is what it would look like if they landed in the United States. So if you put yourself in the mindset of an alien visiting Earth for the very first time, and these are the places that you go, you're going to miss a lot about the history of Earth. You're going to miss a lot about the culture of the people on Earth. The moon doesn't have people, but, geologically speaking, there's a lot that we would miss if an alien did this on Earth. And so just kind of put yourself in that mindset again that, we really barely scratched the surface of the moon. So we do have samples, obviously, that have been returned from the moon. I mentioned that the basalt image on the far left, so that's a meteorite. The one on the far right is from Apollo 16. So that actually is an Apollo image. We have samples from all of the landed Apollo missions. And on the right here, I've got a table with the mission, the year, and then the sample mass that was returned. And as you'll see, Apollo 13 is not there. Apollo 13 did launch to the moon, ran into a little bit of trouble, but they made it safely back, but they did not land on the lunar surface. Each one of these images, or each one of these dots here on the left that have an arrow next to them, are missions that had sample return. So again, we've got the Apollo samples, but then there's little arrows next to 3 of the Luna missions. So 3 of the Luna missions were sample return missions. And here on the right, this is a model of Luna 16. And this arm came out to sample some of the material. So it was only the first about 10 centimeters that it sampled. And then we put it into the sample return container at the top, and it was jettisoned off and came back to Earth. So the Soviets actually did also have samples from the moon in the 1970s, but it's very, very little mass. It's about 3/4 of a pound was returned by those missions. So between 1976 and 2020, there were no sample returns from the surface of the moon. I mean, we've collected meteorites since then, but no samples have been returned from the moon until Chang'e returned some in Chang'e 5, and I clearly miscoded this as green instead of yellow. That should be yellow. All right, so one of the reasons why they're all on the near side is that we needed to be able to have communication with the crew in terms of Apollo. The other reason why they're all on the near side is in terms of where we're launching from and where things need to be returned to. So if we look at where the Apollo missions were versus the Soviets, some of it, again, has to do with where you're launching from and where you want things returned to. And so remember, Earth is moving, it's rotating, the moon is moving, it's rotating. It's a little bit of a complex problem to figure out. So you might be wondering, though, how big the sample mass actually is. So I know a lot of people don't think in kilograms, so I've got some examples of how big some of these things are. A standard suitcase, if you're going to fly on a plane, your mass, or your weight actually, is limited to 50 pounds. So if you had a full suitcase right at 50 pounds, that would be about 23 kilograms. So that's a little bit less weight, a little bit less mass than what Apollo 11 brought back. If you look at a Bernese mountain dog, really pretty dogs, but we can also use them as an estimate. So they typically weigh between 80 and 115 pounds. So that's between 36 and 52 kilograms. So that's kind of closer to Apollo 12 and Apollo 14. If you had a stacked washer dryer unit, it weighs about 238 pounds, which is about 108 kilograms. So that's a little bit less than what Apollo 17 brought back. So as we continued with the Apollo missions, we brought back more and more samples. And it's because the crew was out on the surface for longer periods of time. And then in Apollo 15, 16, and 17, they also had a rover. So they were able to travel much further and collect a greater diversity of samples, which was really important for us to be able to understand what's happening on the moon. This is in stark contrast to the Luna missions. So the Luna missions, if you took all 3 of those together, of an equivalent mass would be a soda can. A full soda can, but still a soda can. Okay, so, but remember, these were robotically delivered sample returns, which is really impressive that we were able to, or the Soviets were able to do that. And then recently, the Chang'e 5 mission in 2020 brought back enough mass that was about the same as a steam iron. So to give you some context of how many samples we really have to learn from on the surface of the moon. Now, in terms of other types of information, we don't have just samples. We also have orbiters, satellites. So here's some examples of some of the information that we have learned from satellites and from orbiters on the surface around the moon. There have been a lot. So this is just going to barely scratch the surface. That's where the basalts are, most of the basalts. So we can see already right away that there's compositional variation. Even if we just look up at the night sky and we say, oh, there's basalts. Oh, there's anorthosites. The basalts are not all the same. So in this big area here, we can also see that there's a range in the iron content. We can also look at thorium. Thorium is a tracer for another chemical composition that we see in samples from the moon called creep. In fact, if you have a sample that has this chemical signature, we say the sample is creepy. Anyways, what is creep? Creep stands for potassium, rare earth elements, and phosphorus. So it's a particular chemical signature that we see, and thorium, again, we can use to kind of model that. So again, we can see some areas that have higher thorium than others, and then same with potassium. Okay, so we can again see that there's a difference in the chemical composition between the near side and the far side, but also even among the basalts, they're not all the same. On the far side of the moon, you probably see this concentration here of iron, and that's not actually basalts. What's really interesting about the far side of the moon is that it's the site of a very, very large impact structure. We can see that over here on the right. It's this feature here, and this is called South Pole Aitken Basin. And South Pole Aitken Basin, when it formed, it was such a large impact event that we believe that it probably excavated the entire crust and exposed some of the mantle. So that's why we see a little bit of a stronger iron signature. Here on the right, we've got crustal thickness. So this was from a gravity mission that was around the surface, around the moon. We've got cool colors are low crustal thickness, and high colors, warm colors, are high crustal thickness. So again, we can see here we've got this hole, and that's South Pole Aitken Basin. And around it, we've got some higher crust or thicker crust. And so that's where some of the material was excavated onto the surface of the moon. We can also see thin crust areas that are corresponding with some of those features where we have really large basalts or volcanic rocks on the surface of the moon on the near side. Well, those are all circles, and those are forming in very, very ancient impact craters. And so we can see that in the crustal thickness really well. So if we use the samples and we use lots of different orbital data sets, how can we learn about the moon from that? Some of it uses a lot of computer models. Some of it is in a lab looking at isotopes of samples or general chemistry, or like what I do. I look under a microscope. I spend most of my time in my research is using different types of microscopes to learn about what is happening at the fine scale. What do I mean by a large impact event? Potentially something about the size of Mars orbiting Earth. Now, some people will say, well, why don't I see the evidence of this on Earth? Well, it was really early in Earth's history. We don't really know what the crust was like, if there was a super solid crust, but also this was a very, very large impact event, lots of energy, lots of heating. And so we've probably eliminated that evidence. But we also have plate tectonics here on Earth. And plate tectonics are great. They do a lot of wonderful things for recycling the crust. So crust, the top surface of Earth that's very, very old is unusual to find because most of it's been recycled. On the moon, since we don't have plate tectonics, we have recorded a very large portion of inner solar system history. So not just the moon's history, but also Earth's history. If we look at the whole scale of the solar system, Earth and the moon are almost in the exact same spot. So anything that happened to, and we think the same thing probably happened to the moon. Same thing happened to Earth and all the terrestrial exposing a portion of beneath the crust that has a lot of iron in it. And if we look at this model over here, we can see that the mantle has a lot of two types of minerals called olivine and pyroxene, which we also have here on Earth. And we have a lot of olivine in our mantle on Earth as well. We also have learned that the moon was once volcanically active. Now, if we put our minds back way, way, way back in time with the ancient people who are looking up, ancient philosophers looking up at the surface of the moon, and they saw these dark splotches, and they said, oh, well, maybe these are oceans, these are seas. And so those dark areas are actually called mares or basalts. But by looking at some of the characteristics on the surface of the moon, we get information that, okay, you know what? I think this surface is a little bit younger than another, and I'll talk about that in another couple slides. We also, from orbital data, not from samples, have learned that there's other types of volcanism on the moon that's just kind of a little bit weird. So this one is a pretty well-known one, in particular on the right. This is Ina D. It's called an irregular mare patch. Remember, mare is what we call those big areas of. This would be like if you made pancakes and you had pancake batter sitting on top of your pan. That's actually what those dark, smooth areas are. So that's actually higher elevation. But this is a new thing. We don't know exactly how they form. We don't, instrument suite, which is dating an irregular mare patch using a lunar explorer. So that's been selected to fly to the moon. We don't know what commercial provider will be sending it yet. So it is an instrument suite of different capabilities of age dating the surface and taking really high resolution images, for example, of the materials that are at Ina D. See if we can solve that mystery. There's also lava flows on the surface of the moon and channels, lava channels on the surface of the moon. So we know that the moon was volcanically active. The surface of the moon is covered with something called regolith. The closest thing that we can approximate that to here on Earth would be dirt, you know? And this image here on the left is a very famous image. Most people are going to think that this was the very first footprint on the surface of the moon. And it's not. This is actually an experiment. So if you've ever been to the beach and built a sandcastle, you understand that the materials are going to behave a little bit differently if they're dry versus wet. Now, in this case, it's all dry, but we're still able to preserve the boot print. So somehow those particles in the regolith are sticking together. And it's because they're very angular particles and they just kind of stick that way. In the sandcastle analogy, those particles are sticking together because of water and surface tension. But here on the moon, they're sticking together because of the shape of those different particles. They can be very angular. And so this photograph was taken to allow the physical properties people to understand a little bit about what was happening on the surface of the moon. On the right, this is an image of a regolith sample, actually a regolith breccia. So if you took regolith and turned it into a rock, then that's what this is. Again, this is taken under a microscope. You can see some of those angular pieces. You can also see some things that are very, very smooth and round. So these are glass spherules that are found in lunar regolith, and they may have occurred from a volcanic event and thrown up in the air and quenched in glass, or they could also be potentially from impact events. So there's different types that we see. We have been able to determine that activity on the moon has changed over time. So we've got two time blocks here. We've got the pre-Nectarian, which is the 4.5 to 4 billion years ago. And then the nearer present over here on the right. So 4 billion years ago to present. And so this walks through kind of what's happening in terms of the impact events. So these are your large impact craters that you can see, impact basins you can see on the near side of the moon. So they're happening between 3.7 and 4.1 billion years ago. We also have some volcanism that's happening at different time periods, 3.9 to about 1 billion years ago. We may have some volcanism like in the irregular mare patches that are less than 100 million years old. And we also, again, we've got evidence from the surface that we've got younger things. In fact, the Chang'e 5 mission that returned samples actually returned some basalt that was the youngest basaltic sample ever studied. And so it was around 2 billion years old. Here on the bottom, we've got depth. So this is showing the different types of material near the surface versus at depth. And then again, over time. And so you can see that over time, there's different types of volcanism that is happening. We also use impact craters in general to better understand what's happening and how old something is. So if you've had a surface sitting out for billions of years and lots of things are impacting it, it's going to have a lot of impact craters. If you have something that's only sitting out for 1 million years, which is not that long, then it's not going to have as many. So we can use the number of impact craters to give us an idea of how old the surface is. And so that's something that's done with the Lunar Reconnaissance Orbiter. They do some calculations also of how old the crater may be based on the way it looks, how many rocks are around it. And then the crater size frequency, how many craters you have a particular size in an area, can help us to understand how old something is. And we can do that because we also have the Apollo samples. So this whole process is calibrated to the Apollo samples, which have been isotopically dated. The great thing about this is that we can use it to age date the surfaces of other places in the solar system. So if we want to look and see how old something might be on the surface of Mars, we can use crater counting because it all calibrates back to those Apollo samples. So by going to the moon and getting these samples, we actually learn about a lot of other places in the solar system as well. So we've already kind of covered this, but the moon is compositionally diverse. It's not all gray. We've also seen, again, that difference in the basalts, for example, the difference in the near side and the far side in terms of chemistry. But the really cool thing, though, is that you can still look at this and say, but it still looks black and gray. Well, we have some really interesting things on the surface of the moon. So this image here is a microscope image of a soil sample or a regolith sample that was collected in Apollo 17. And you can see the orange particles. And the crew was actually able to see this on the surface. I hope it's showing up in your screen really well. Sometimes with projectors, it doesn't work as well. But this area here, to me, I grew up in Georgia, so I'd say, well, this looks like Georgia red clay, but it's certainly not gray, right? It's not gray at all. And so we've made really interesting discoveries from the samples that there's no way we would be able to have that without going to the surface of the moon. And so this probably occurred through fire fountaining. So volcanic eruptions spraying material up into the air, or not air, into above the surface. We also have in this image, this little guy here, this is called a gnomon. And the gnomon was used for a lot of different things. It was used to calibrate how big things were in a photograph, so we knew how big they were on the surface. You also see a color chart on there, and so that helped us to calibrate the cameras. And then you also see a shadow, and so that is also demonstrating the orientation of sun when each photograph was taken. If we look, we also know that the moon is not dry. So I talked about the image with the regolith and how they're sticking together, not because of water, but because of the angularity. There is actually some water on the surface of the moon, and it's also been measured in samples. Small amounts, but it's there. So this image here on the left, so these are polar images. We've got North Pole and South Pole. And then these green dots are where ice has been detected using several different components of different orbiters. And again, on the right, this is the South Polar region, again, the ice exposures. And this is one of the things that we want to learn more about in Artemis when we go to the South Polar region of the moon is, what is the composition like there? How is it different from what we've been to before? Now, the Apollo 17 mission happened in 1972. Okay, so it's been over 50 years since that mission, even longer since Apollo 11. But what's really interesting is that we still learn new things from the samples. I think a lot of times people say, well, haven't you learned everything there is now? You've been looking at the same rocks for 50 years. Well, we get better techniques and better instrumentation, so we can learn things that we never could have done 50 years ago. And this is an example here. On the left is crew on the Apollo 17 mission that were getting ready to collect a drill core. And on the right, we've got two scans. This is basically a CAT scan of that core in 1974. So you can see where there are some different chunks. And in 2019, it was scanned again. Now, this particular sample was not opened for researchers to be able to work with in the 1960s and 70s, because NASA was smart enough to realize that technology was going to get better, technology was going to change, and that we needed to preserve some material for future research. And so this is part of a program called ANXA, which is the Apollo Next Generation Sample Analysis. And on the bottom are some of the curation staff going through the core and taking notes of that and pulling out some materials. The woman here on the right is Juliana Gross, and she has just become the Artemis sample curator. So when the Artemis samples come back, she's going to be the one in charge. All right, so what's left to learn? We've learned so much about the moon. There's still a lot to learn. We don't know nearly enough. There's, lots of compositional diversity and things like that. But, what is it that's going to be happening next? So this is just a little bit about the Artemis campaign that I'm going to focus on. But if y'all have questions about other parts, you can ask that too. So we call it the Artemis campaign instead of the Artemis program because the Artemis campaign really includes lots of different programs. So the Orion program, Orion is what the crew will be in, that has its own program. So Artemis campaign is a little bit more encompassing. We've already had Artemis 1. So that flew to the moon last year, late last year, and flew back. That did not have any humans on it, but it did have moonikins, not mannequins, moonikins, to detect how radiation might affect those bodies. Artemis 2 should be occurring next year, and those will have humans. That crew has been selected. They will not go to the surface of the moon, but they will go around the moon and come back. Very similar to what happened in Apollo 8. There were other Apollo missions before Apollo 11, and they were laying out all the different steps that they needed to make sure that they could do before they actually landed. And then Artemis 3 over here, Artemis 3 is going to be the first human landing on the surface of the moon, and probably taking place 2025 or later. There are specific things that the crew is going to test. So they're going to test the new launch system. They're going to test the new space chutes. They're going to deploy different instruments. So a seismometer, for example. The Apollo astronauts also deployed a seismometer, and that's how we know that the moon has moonquakes. They're going to collect a lot of different samples. Science that Artemis 3 has as goals. And within each one of these goals, there's lots of specific objectives. So we want to learn about what's happening on other planets. We want to learn about volatile material, so water. How is it impacting Earth? Okay, again, if something is, we have the record on the moon that we don't have on Earth in terms of we don't have plate tectonics. So we can look at that. We can also look at what has happened with the sun over time. So there's a lot of different science goals that we can have from collecting those samples on the lunar surface and also deploying instruments. This is an image that'll show how they're going to bring the crew to the surface of the moon. So it steps through all the different components. It will bring 4 crew to the moon. So in Apollo, there were 3 crew on each mission. 2 went down to the surface and 1 stayed in orbit. In Artemis 3, you're going to have 2 stay in orbit and 2 go down to the surface of the moon. So that crew has not been announced yet. So we're looking forward to when that happens, and those will become our new celebrities, just like Apollo. I've just got a couple slides left, and then I'll answer some questions for y'all. Where is Artemis 3 going to go? It's going to go towards the south polar region of the moon, an area where we have not explored at all. In terms of humans, we don't have samples from there. We have crashed a few things into the surface of the moon down there. We've got some orbital imagery, but we have not sent humans. And so there's 13 different regions where NASA is looking to land, and not a landing site. These are 13 regions. So they're about 15 square kilometers of space. And so when they select a region, then they'll select a landing site. And it had a lot of considerations that went into it. So how close was it to the pole? Did it have enough daylight? Was it gentle enough slopes to where the astronauts could actually walk around? So there were a lot of different things that went into these 13 landing regions. Oh, and this is fun. This is just to make you feel small and insignificant in a good way, to give you a perspective of how big some of these things are. At the South Pole, we have a crater called Shackleton. So that is named after the explorer on Earth that went to the South Polar region. And this is a cross section of Shackleton. So it's a little over 4 kilometers wide, 4 kilometers deep, and a little over 21 kilometers wide. So if you put that into context of the Grand Canyon, I'll give you a second so you can think about how big you think the Grand Canyon is. Okay, I bet you're wrong. That would be the Grand Canyon to scale with Shackleton Crater. It completely dwarfs the Grand Canyon. So if you've been to the Grand Canyon and you've stood on the edge and you're just completely overtaken by how massive it is, think about what that tiny little crater at the South Pole looks like. All right, this is my last slide. So I have to end with samples because I am a sample scientist. I mentioned all the different science goals that Artemis is going to have, and a lot of it comes back to the samples and what we can learn. So we're going to have different types of rock samples, different types of regolith samples that are going to come back from the South Polar region than we did from the near side. So with the near side, most of those Apollo sites were in an area with basalt. Apollo 16 was in an area that was hardly any basalt at all. It was almost all anorthosite. Down at the South Polar region, it's probably going to be mostly anorthosite as well. But again, we've got compositional diversity. We've got volatiles that are down there. We don't know how that's going to impact the regolith and how that's going to be preserved. So there's a lot of things that are going to be really exciting for the South Polar region because we just don't know a lot of it. So many of us are looking forward to getting those samples back. I'm very glad that some crew is going to do it for me. I do not want to go. That's a question I often get. Do I want to go be an astronaut? No. There are better people than I to do that. So anyways, that was my last slide. So I'll stop sharing. And then Chris, if there's any questions, we can get to those.
Well, first, I'll encourage everybody to give you a great big round of applause. They can drop little clapping hands emojis in the chat for you because that was fantastic. Thank you very much.
Yeah, you're welcome.
I mean, so much. The moon's a pretty cool place.
It's a little bit of an interesting place, yeah.
Because there seem to always be new science coming out about them, even though it's 50 years. We're 50 years past, like the first landing. And like I just love the photo that you shared of like kind of like the next generation of scientists. I guess we're even beyond the next generation who are like still in the box, in the gloves, pulling out Apollo samples and continuing to just expand our knowledge of the Earth Moon system. I think it's awesome. Well, viewers, let me remind you, go ahead and drop your thoughts, your questions into the chat for Dr. Fagan. I know that you've got some, so go ahead and be typing those up. But Amy, can you tell me a little bit about what brought you to moon science? Because I've had a chance to talk to, like, I saw a photo credit from like Clive Neal in your talk, and like I've had a chance to interact with Dr. Neal and hear his story, but I'm interested in yours too.
Sure. So it was actually an accident. I went to graduate school. Well, actually, I guess we can back up. For the longest time when I was a kid, I wanted to be a veterinarian at a zoo, and I wanted to work with the large predators. So the wolves, the big cats, the bears. And I got to a certain point in high school where I was taking a lot of honors and AP classes, and I was feeling a little bit burnt out. And I said, I don't think I want to go to vet school anymore. That's just too much school. And I just want to go to college and get my degree and join the workforce. So what do? I go and get a PhD, which took me an extra 6 years after college. But yeah, I kind of stumbled into geology. Excuse me. That was my timer to make sure I didn't talk too long. I stumbled into it. I was looking at a course catalog and I found some really interesting courses, and it was, wow, that's a class. That sounds really cool. And so that's how I got into geology. What interested me in planetary geology specifically was a 1-credit class I took my freshman year of college that was about the asteroid impact theory for the extinction of the dinosaurs. And the day that we talked about impact craters themselves, that was it for me. I saw an impact crater. I was like, that's it. This is what I want to do. So I actually went to graduate school at Notre Dame to study impact craters on Mars. And then through, a series of events, had ended up having to change advisors. So I went from studying geomorphology on the surface of Mars to studying samples from the moon with Clive Neal. So it was a very happy accident, but it was an accident. It was one of those things where at the time it was very stressful because it was not what I had planned, and well, there's plenty of sayings for, when things don't go planned. So it was a great accident to have that happen. So.
Oh, I love that. That's a great story. That's fantastic. And so what uh apologies if I missed like a citation. I'm curious as to what your research on these samples and on lunar exploration in the Earth Moon system has been, or maybe what you're working on right now, what your explorations are.
So sample scientist, so I look under a microscope. And mostly what I've recently been doing is looking at the compositional diversity of meteorites from the lunar surface. So specifically, they're regolith breccias. And regolith breccias, again, are made out of the regolith that kind of get adhered together and turned into a rock. And so because meteorites come from anywhere on the lunar surface, anywhere where there was a large enough impact to eject the material to go faster, or at least at the escape velocity of the moon, it holds lots of different particles in it that you can learn a lot about. The other really interesting thing about regolith breccias is it preserves whatever is hitting the regolith. And in that case, it can also mean teeny tiny little micrometeorites from what was hitting the lunar surface. And so we have this recorded in some of the Apollo samples. I think it's also been found in some of the meteorites as well, that you can find micrometeorites, things that are about as thick as your hair, but are compositionally distinct and isotopically distinct from lunar materials. And some of them we can actually connect back to, okay, I think it came from this type of material. Some of it we cannot. So that's another thing that I have worked on in the past. But currently, I'm actually part of that DIMPLE team. So that team that is sending an instrument suite to go investigate INA. So I am one of the scientists on that team. So I'm kind of branching off into kind of the exploration realm of things a little bit as well, a little bit beyond my microscope.
Oh, exciting times.
It's very exciting.
Yeah, that sounds great. Thank you. So a question that's coming for you: about when did the Earth impact occur that resulted in the moon? You said it was early Earth's history, but
yeah, it was about 4.5 billion years ago. So you're talking about, tens of million years after the formation of Earth. But if you think about that, where do you draw the line of, okay, Earth is formed, right? Because that, when we look at a geologic timescale, I mean, I think in billions of years. Most humans don't think that way. So to me, on a geologic process, anything that's less than 1 billion years old is really, really young. We know approximately how old Earth is, not necessarily actually from studying Earth rocks, but from studying meteorites from other places. So there's a type of meteorite called a chondrite, and chondrites have little spherules in them called chondrules. And those represent some of the early forming material in the solar system. So you can think of it as Dippin' Dots. Everybody's had Dippin' Dots, or at least seen them, right? They do that weird thing sticking to your tongue. So if you have Dippin' Dots are the chondrules, and these are the early forming material in the solar system history. And then they just smash into each other and smash into each other and smash into each other. Eventually, you're going to get something that grows bigger and bigger and bigger. And so we think that the rocky material in the inner part of the solar system was formed that way. So from this process called accretion, where you have all these chondrites smashing into each other and eventually building it bigger and bigger and bigger. So we know the approximate time or the age of Earth and the moon from looking at chondrites, but also from looking at some of the oldest samples that we have from the moon. So the samples that we have from the moon, we have samples that are older than what we have here on Earth. And that comes back down to plate tectonics.
Okay, got you. Good question, David. Another viewer wants to know if you've ever been to the Alder Planetarium in Chicago, which leads me as a museum person to want to know, like, what's your museum visitation schedule for traveling around?
So I think I have, but it was when I was very, very young. I have family in Chicago, and we used to go up when I was a kid. Again, I grew up in Georgia. So we used to go to Chicago when I was a kid and have family reunions. But I do really like the museums in Chicago. I love the art museum in Chicago. That was one of my birthday presents once when we were in graduate school. So my husband and I were in graduate school at Notre Dame, and you don't have a lot of money when you're in graduate school. So that was my birthday present, was to go on the train and go see the go to the art museum. So I love museums. I am really looking forward to my youngest daughter being old enough to really appreciate museums so that we can actually go to museums. Out here in Western Carolina, there's not a ton of museums, but we do have some really interesting mountain heritage out here. And so we actually have a small little museum about mountain heritage out here. But yeah, I don't go to museums as often as I wish I did.
We just recently here at our museum a couple of years ago got a lunar meteorite
Nice.
that went on display, which you mentioned was sort of part of what you had been looking at and working on. What's the science that comes from something like that? I mean, we have the Apollo samples, and so we can see a lunar meteorite and say, oh, we're pretty sure this came from the moon. This looks like that. But these lunar meteorites must come from like such different time scales and time periods and histories.
Right. So the image that was on the left of my screen, so that was a basaltic meteorite, and that was about 3 billion years old. So we age dated it, and it's about 3 billion years old. At that time, when that sample was age dated, it was one of the youngest basaltic samples that we had from the surface of the moon. There are a few other meteorites that are around that age, but until those meteorites were found, we had a very different idea of what the cooling history was and the volcanic history of the surface of the moon was before those were found. So when China brought back their sample and it was significantly younger, again, that's kind of rewriting what we think is happening on the moon. And from all of our samples and from our orbital data, we know more about the moon as a planetary body than we do pretty much anywhere else in the solar system. So we can take what we learn in terms of the process that the moon formed or differentiated into layers, and we can apply that then to potentially how other places formed as well. So the samples from the meteorites are great, again, because they don't have that bias from being on the near side. So they tend to have different ages than what we have on the near side. So we can get a greater variety of chemical composition. We can also get a greater variety of ages that help to fill in all those different gaps of what was happening over the timescale of lunar history.
A question from the chat for you.
Okay.
About, how does isotope ratios on the moon differ from those on the Earth?
So some of the isotopes that they use to identify that, okay, this probably formed from Earth is with oxygen isotopes, and they're almost identical. For a long time, it was said, okay, no, they are exactly the same. And now we know that they are slightly different because the instrumentation has gotten better. But that's predominantly what they're using. So we can use that as a signature that, yes, it came from Earth. There are a lot of different isotope systems that we use for various different things on the moon. So, for example, different age dating. Some folks use lead. The sample that was on my screen, that was dated from argon analyses. So actually the isotopes in general, that was one of our key things that helped to point to a giant impact theory for the formation of the moon.
Good question, Glenn. All right, let's see what else we've got for you. You briefly mentioned moonquakes, which I've heard of, but when I think about them and I hear you say things like that, the moon doesn't have tectonic action, it makes me wonder how a moonquake happens. What makes the moon vibe and shake when it's inert? There's nothing going on, or seems like there shouldn't be anything going on.
Right. So we actually have tectonic activity or tectonism on the moon, but we don't have plate tectonics. So the tectonic activity is more of like things shifting, but two ways. One, the moon is cooling down, and when it cools, it goes and it's creaky.
Okay.
So some of that comes from that. And the other thing is that the moon does not have an atmosphere. So if any sort of material is coming at the surface of the moon, it is going to go straight down and hit the surface. See, here on Earth, we've got the atmosphere that, when you look up at the night sky and you see a beautiful shooting star, that's actually just a piece of a rock that's melting. Kind of ruins it for you. for at least it did for the third graders that I told last week. But so here on Earth, we've got that, right? So we are limited by how much material is actually hitting the surface. On the moon, we don't have that. So some of those moonquakes are also from impacts. And we know that impacts are still occurring on the surface of the moon, not to the size of those large impact basins. But we can see the evidence in terms of the orbiters, where there will be no impact crater there in one image. And then a few years later, there's an impact crater. We can also observe it from Earth in terms of a flash. So there's a lot of energy. Even a small impact, it's going to have a significant amount of energy. That's material is moving really fast. And some observatories here on Earth actually measure that, and they see when a flash occurs, and they can kind of triangulate where that occurred on the surface. And then they start looking through the images from the Lunar Reconnaissance Orbiter camera to kind of see, okay, well, how big is it? So they can connect it. It's pretty cool.
Oh yeah. And weren't recently in the last few years there were missions to like artificially bombard the moon, like launching shells and canisters at the surface to cause plumes of material in order to study them. And
so that was towards the South Polar region. So that impacted into Cabeus crater. And so it's a crater that's almost entirely in shadow all the time. And so it impacted into Cabeus, and the material that came up, then another orbiter was able to detect the chemical composition. So that's some of the information that we have that, yes, okay, there are volatiles at the South Pole. So when I'm talking to my students, I say, well, actually, you know, planetary scientists in many ways are really just grown up kids, because we really like to smash things into other things to see what happens. And it's not the first time that NASA has done that. They have impacted something into a comet before to, again, measure the plume and what it was. They've flown something through the tail of a comet and brought that material back, tiny little particles the size of dust. So there are ways that we can learn about the moon and other planets and other planetary bodies by excavation. And you excavate things by smashing stuff into it.
I love it. All right, I think this will be the last one for you today.
Okay.
How large are the largest rocks that have recently hit the moon?
Oh, that's a great question, and I don't know off the top of my head. I would hate to tell you the wrong thing, but you can pretty easily Google impact craters, like new impact crater on the moon, and you should be able to see some of those images. And from the size of the impact crater, so how wide the diameter is, they can back calculate how large the rock was that hit.
I think the internet's got the answer for you out there, David. Give it a search. Maybe report.
I don't want to say the wrong number.
Sure, yeah. Well, Amy, this has been fun. Thanks for joining us today on the program.
You're welcome. Thanks for inviting me. I always like talking about the moon, and it makes me really excited. And now I'm just going to be jazzed all day because I got to talk about the moon this morning.
I mean, the only thing left to do is to go out tonight and just take a moment to look up at it, right?
Mm-hmm. Yeah, and just appreciate it. Like, oh, you know what those dark splotches are and the light splotches, and also that there were people there and that they actually still left a lot of stuff behind. So there's stuff left on the surface of the moon because of humans being there. And that's such a cool thing to think about.
I love it. It's fascinating stuff. The folks in the chat are sharing their appreciations for you as well. So thanks for being with us. And viewers, I hope that we'll see you again here next year. This will be with the last program for 2023, like we said at the top. But come back and see us again in January. We'll be here with the Lunchtime Discovery Series from the Office of Environmental Education and the museum, bringing you more interesting people doing interesting things out there. We're going to do a whole lot of great learning and sharing here at the Lunchtime Discovery Series. So don't miss out. If you want to stay in touch, make sure that you head to naturalsciences.org. That's the museum's website. There you can find out about upcoming programs just like this one, or you can head to the Office of Environment, and you can go to the Office of Environmental Education's website, eenorthcarolina.org. You can actually sign up to get the email newsletter for this program specifically. That way you've got the link in your inbox. You can just click and join us here on YouTube almost every single Wednesday. So don't forget, You can watch archive talks on their website as well. A lot, dozens and dozens and dozens of presentations from awesome scientists and educators that you can watch and take in. There's a great archive and a library there that's available to you. So, you know, if next Wednesday rolls around and you're looking for something to do and we're not here live, go check out the playlist. There's a lot there for you. Thanks for sharing with us today. Happy New Year, everybody. Happy holidays. We'll see you again soon. Bye, folks.